Today we're going to be talking about simplifying radicals without variables, and then the next video we'll be talking about simplifying radicals with variables. And what do we mean by a radical? So a radical, the most common kind, is a square root, but it can also include cube roots, fourth roots, fifth roots, whatever sort of roots you want. And for a root, what you're doing is you're basically undoing a square. So, for example, the square root of 2 squared is just 2. They sort of cancel each other out, if you will. The cube root of 2 cubed is also just 2. The fourth root of 2 to the fourth is 2. The fifth root of 2 to the fifth is also 2. Now, typically, you're not asked about it in that way, though. Instead, they may say square root of 4. Well, 2 times 2 gets us 4, so that's 2. Cube root of 8. Well, 2 times 2 times 2 gives us 8, so that would also be 2. Fourth root of 16. Well, 2 times 2 times 2 times 2 gives us 16, so that's 2. Fifth root of 32. Well, 2 times 2 times 2 times 2 times 2 gives us 32, so that's 2. So in order to recognize a lot of these square roots, cube roots, fourth roots, etc., it's going to be helpful to recognize what a lot of the common squares, cubes, fourths, etc. When we say largest perfect square, that is dealing with any of these ones that simplify nicely. So we're talking about square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4, square root of 25 is 5, because 5 times 5 is 25, 4 times 4 is 16, etc. Similarly, knowing a lot of your perfect cubes would be helpful as well. And then you can even go crazy and know your perfect fourths, perfect fifths, etc. Also note that some of these are going to make sense with negatives and some aren't. Because in particular, if you square fourth or any other even power a negative number, it turns positive. So it does make sense to ask for the cube root of negative 8. That would be negative 2, because negative 2 times negative 2 times negative 2 gets us negative 8. It would not make sense to ask for the square root of 4. That's not going to be a real number. So that's something that's always worth keeping in mind. Or the cube root of negative 16. Sorry, it doesn't make sense to ask for the square root of negative 4. I might have said positive 4. Square root of positive 4 is 2. Square root of negative 4 is not a real number. Square root of the fourth root or square root of negative 16, also not a real number. So if you're going to have negatives, you want to make sure that you are dealing with strictly negative powers, because all of those negative numbers squared become positive. Negative numbers cubed are cool. Negative numbers to the 5th power are also cool. Those will stay negative. 7th power, 9th power, etc. So let's go ahead and practice identifying those now that you've sort of gotten a big picture overview of how a lot of these roots work. What would be the square root of 64? Well, 8 times 8 gives us 64, so that's 8. Well, square root of 25? Well, 5 times 5 is 25, so that's 5. Square root of 121? 11 times 11 is 121, so that's 11. For the square root of 1 over 81, well, what you can do is separately take the square root of 1 and square root of 81. It's cool to distribute that over division. Square root of 1 is 1, square root of 81 is 9, and indeed 1/9 times 1/9 gives us 1/81. We often will talk about the positive square root of a number and the negative square root of a number. When we say negative square root, we mean negative 1 times that square root, because by definition, we define the square root to be the positive number that times itself gives us the original. It's also sometimes called the principal square root for that reason. And that's just in order to make it a function, in order to make it have one answer, because technically, both 2 times 2 and negative 2 times negative 2 are going to give you positive 4, but we want just a single answer for this question, so we just define it to be the positive number that times itself gives you that number. And this is just, again, another reminder that if you had a negative under a square root, that does not exist because there's no real number such that times itself gives you a negative. So let's go ahead and practice a little bit more with square roots. So I encourage you to pause this video and try these yourself, and keep in mind that sometimes does not exist will be an answer. So for this first one, I would recommend changing that decimal to a fraction. Then I would note that the square root of 1 and square root of 4, you're allowed to distribute that square rooting over that fraction. Square root of 1 is 1, square root of 4 is 2, and your final answer would be 1/2, since 1/2 times 1/2 gives you 1/4. This next one, we're going to again exploit that we can distribute that over the fraction. Square root of 49, 7 times 7 is 49, so that's going to be 7. 12 times 12 is 144, so that's going to be 12. For this next one, be careful. You are not allowed to distribute square rooting over addition. So I'm actually going to write that explicitly. So you can distribute a square root or any root over multiplication or division, but you cannot do so over addition or subtraction. So in particular here, we would first have to simplify. 144 plus 25 is going to give us 169. And the square root of 169 is 13, since 13 times 13 gives us 169. And if you don't believe me, had I tried to distribute this is super illegal math. Square root of 144 is 12, square root of 25 is 5. 12 plus 5 does not equal 13. So that just to prove to you, it's not going to work to distribute it over the addition. You have to simplify under the square root first. For this next one, keep in mind that negative chilling out on the outside is really a -1. So it's saying -1 times the square root of 4. Square root of 4 is 2, since 2 times 2 gives you 4. -1 times +2 gives you -2. For this next one, however, the negative is underneath the square root itself, and that's a problem because there is no number in the universe that's whenever I multiply it by itself, it gives me a negative, because a negative times a negative is a positive, positive times a positive is a positive. So that does not exist. Similarly, order of operations wise, this next one has the exact same problem because we have a negative under a square root. So that still does not exist. We talked about this a little bit earlier, but keep in mind that we can have any type of roots, not just square roots. So square roots, there's sort of an implied 2 on that root because it's saying what number times itself gives me that number, what positive number times itself gives me that number. But we can have cubed root, which is saying what number times itself 3 times gives me that number. Fourth root, what number times itself 4 times gives you that number. And whatever is that number is known as the index of the radical, and that tells you how many times you have to multiply in order to get that. The radicand is going to be known as that number underneath the root, and then the radical sign is known as that root itself. Keep in mind the general pattern that we touched on earlier, that if I multiply any sort of number by itself an even number of times, it's always going to be strictly positive, because if I take a negative times a negative, that becomes a positive, and if I do that in as many groups of 2 as I want, I'm still going to wind up getting a positive. Versus I can have odd number of times and multiply a number by itself and it actually gives me an answer. So in particular, what you care about is if I take the nth root of negative something, let's say -8, that's going to exist if n is odd. So for example, the cube root of -8 is going to be -2 because -2 times -2 times -2 gives us a -8. Similarly, the cube root of -64, that's going to give you -4 because -4 times -4 times -4 gives you -64. And if I had the fifth root of -8, that would still exist. I don't know what it is, but it will exist because if you take a negative number times itself an odd number of times, you're going to be back to a negative and you're going to be fine. Versus if I have some sort of negative underneath a even root, It does not exist if n is even. So in particular, if I had the, let's say even fourth root of negative 16, that's not going to work because negative 2 times negative 2 times negative 2 times negative 2 gives us positive 16. So that does not exist. So that's always something you want to be careful of. So we can only have negatives underneath the root if that root has a negative, has a odd power to it. So an odd index, I should actually say. It's not index to it. And that's what this is sort of saying in more words, that if we have a negative number, it's only going to actually end up being the case that the, let's say, cube root of negative 2 all cubed. This is what this is sort of saying in words, versus the fourth root of negative 2 to the fourth. Well, order of operations wise, you would simplify underneath the root first. Negative 2 cubed gives you negative 8. Cube root of negative 8 is negative 2, exactly equal to negative 2 as is. Versus negative 2 to the fourth, well, when we multiply negative times itself 4 times, we're going to be to a positive, and that ends up equaling 2. So this is sort of noting that once I have taken a negative number times itself an even number of times, I'm going to be to a positive. That's all this is really saying in more words. So how are we going to simplify radicals entirely? So we want to make sure that there are no factors that can be written as powers greater than or equal to the index. So we want to basically pull out all of the perfect squares, perfect cubes, etc. that we can. And then we want to make sure that the radicand itself doesn't have any fractions. We're going to have to clear any fractions that are in the denominator, or any numbers in the denominator that still have a radicand on it. And that process is known as rationalization, which we'll be going over shortly. So sometimes you have to rationalize, sometimes just when you simplify, the radicand goes away and then you're good. And that's making sure that no radicals are appearing in the denominator. And just as a reminder on the vocabulary, the radicand is that number underneath that root. So it's actually kind of tomato to talk about number 2 and number 3. So let's go ahead and simplify some of these radicals that have higher ordered powers. So for this first one, we have the cube root of negative 8. For the cube root of negative 8, you're asking yourself what number times itself 3 times gives us negative 8, which in this case would be negative 2 times itself 3 times. So that would equal negative 2. Again, negatives underneath an odd-powered root, such as 3, 5, 7, etc., are fine, because once you do a negative times yet another negative, you're back to a negative. For the fifth root of 243, we're looking for something times itself 5 times to give us 243. And for these higher power roots, this is where I like to break out factor trees. I know in particular that the number 3 is going to go into 243 because all of the digits add up to a number divisible by 3, in this case 9. In particular, 81 times 3 is going to give us 243. 81 further breaks down into 9 times 9. And 9 times 9 breaks down to 3 times 3. I also like to find it helpful to perhaps in another color actually cross out those middle steps, just so I don't accidentally consider that part of our factorization. And now we see that 3 times itself, in this case 5 times, is going to give us 243. So the fifth root of 243 is going to be 3. Similarly, for the fourth root of 81, well, we actually, in our previous factorization, just saw that that's going to be 3 times itself 4 times. And that negative chilling on the outside is okay, because in terms of order of operations, that's a negative 1 times the fourth root of 81. And the fourth root of 81 we just established is 3. So this gives us a total of negative 3. For this next one, this is where you actually want to be careful, because it would be really, really tempting to just cancel this out and say, oh, that's going to give us negative 2. But then if we do a little sanity check here, well, there's no way that the fourth root of anything is going to give us a negative. And in terms of order of operations, what do we want to do? We want to take the fourth power of negative 2 first, which in this case is 16, positive 16, because when you do a negative times a negative, you're to a positive times yet another negative, you're to a negative, but times yet another negative, you're back to a positive. And the fourth root of positive 16 is 2, so be careful about that. Versus on this next one, when we're doing the cube root of negative 7 to the third power, well, there we have a negative times just one more negative. That's going to get us back to a negative. Or if you wanted to formally first find the negative 7 cubed and then cube root it, you would again get back to a negative 7 as well. For this next one, I'm definitely going to want to make a factor tree, and in particular, I noticed that he ends at a 5. So I know that at least 5 has to go into 9,375, and I'm going to just do that division off to the side here. It looks like 5 times 1,875 gets us that. 1,875, that actually looks like 75 in particular might go into it, so I'm going to test that out to the side here as well. Let's see. And it looks like in particular 25 times 75 gives us that. And then if I break down 25, that's going to break down to 5 times 5. 75 is going to break down into 3 times 25, and then 25 breaks down to yet another 5 times 5. So I'm actually going to explicitly write that prime factorization and cross off those middle steps, because I don't want that part of my prime factorization here. So it looks like in particular that we're going to have a 3 times 5 to the 1, 2, 3, 4, 5 fifth power. So I'm actually going to break that down into 5 squared and 5 to the third, because I already kind of know I'm wanting to break out a cube root of some sort. Then I'm going to break that down into 3 separate cube roots. So we got the cube root of 5 cubed, the cube root of 5 squared, and the cube root of 3. The cube root of 5 cubed is actually going to bring us back to 5. 5 cubed is 125. The cube root of 125 is 5, because 5 times itself 3 times gives us 125. For the remaining part, cube root of 5 squared is not going to simplify. Cube root of 3 is not going to simplify, so I'm just going to go ahead and multiply 5 squared times 3 to give us the cube root of 75 is what's left underneath that cube root there. Then we want to keep on going with these next two. So for this next one, we want to do ourselves a sanity check. We've got the negative underneath the fourth root. So that is asking what number times itself 4 times gives us a negative 16. And that's actually just not going to exist. That's not a real number, because there's no way to multiply a negative times itself 4 times and somehow be back in a negative. For the next one, we're going to be able to distribute that square root over the numerator and the denominator. For the numerator, it looks like because the digits add up to 12, which is divisible by 3, they should be at least divisible by 3. So if I break off to the side here what 147 divided by 3 is going to give us, 147 breaks down into 3 times 49, and 49 breaks down into 7 times 7. So I'm going to rewrite that as the square root of 7 squared times the square root of 3, all over. For 75, we already previously established as the same thing as 3 times 25, and 25 is 5 times 5, so that's going to be the square root of 5 squared times the square root of 3. Square root of 3 divided by itself is simply 1. Square root of 7 squared is going to be 7. The square root of 5 squared is going to be 5, for a final answer of 7 fifths. So for these larger numbers, it can help to prime factorize it. And then once you notice that you have the same power on the same index on the root as you have power on the exponent, then you'll notice that that will either cancel to make the exact same thing whenever that is an odd index / odd exponent, or cancel to make the absolute value of that if it is even, because for the even ones you're going to want to make sure that that number remains always positive at the end of the day. And it can help to actually just literally do out the math like we did in 14 if you are in doubt. So let's go ahead and talk a little bit more about rationalizing denominators. So rationalizing denominators is whenever you want to clear any radicals out of the denominator. And how do you do that? Well, if, for example, you have the square root of a in the denominator of something, if you multiply both the numerator and denominator by square root of a, you're really just multiplying by 1, which is fine, and then you'll wind up with a square root of a squared down there in the denominator, which will just leave you with an a there in the denominator. And a lot of times in math we find it more aesthetically pleasing if that denominator is simply a number rather than a root of some kind. So let's go ahead and simplify these. So for this first one, we notice there's a square root of 2 in the denominator, so we're going to want to multiply both the numerator and denominator by 2. That's going to make that numerator into square root 3 times square root 2, and that denominator becomes the square root of 2 squared. Square root of 2 squared will simply leave us with 2. Square root of 3 times the square root of 2 will give us the square root of 6 because we can recombine those underneath that root. And then 12 divided by 2 will leave us with 6 on the outside there, since 12 over 2 normally simplifies to 6, so our final answer would be 6 root 6. For this next one, we're going to multiply. Actually, before we start multiplying, I think that we're going to go ahead and actually simplify the square root of 512. So if we simplify the square root of 512, we notice that in particular this would be even, so 2 certainly goes in, and all of the digits add up to something divisible by 3, so I know 3 also goes in, and if both 2 and 3 go in, I know the 6 is going to go into this number. So off to the side, I'm going to do 512 divided by 6. And actually, I am a liar, potentially, on that. Oh, wait, no, I was wrong about the divisible by 3. 5 plus 1 plus 2 is 8, and 8 is not divisible by 3. That was brain fart of me. So 2 goes in, though. We know that. So let's go ahead and just divide it by 2 off to the side here. So if I divide 512 by 2, that gives us 256. 256 I know is further divisible by 2, so I'm just going to divide by 2 yet again. That will give us 128. 128 I know is also divisible by 2 yet again. Divide by 2. We're going to get 64. 64 I know breaks down to 8 and 8, and I know that's not technically prime factorized, but I think it is factorized enough in order to simplify that root because I've already gotten 8 times 8 in particular. So I'm going to rewrite this as 8 over the square root of 8 squared, that covers the 2 8s, the square root of 2 squares covers those 2 2s, and then the square root of 2, that final 2. Square root of 8 squared is going to just become 8. Square root of 2 squared becomes 2. Square root of 2 stays as is. And we've got the 8 here. And then when I do 8 divided by 8, that's just going to leave me with 1. So I have 1 over 2 root 2. Now this is ready to rationalize, now that I've got this down to simpler numbers. So in particular, I'm going to multiply both the top and the bottom by square root of 2. Notice how I don't have to multiply it by 2 root 2. I can just do by square root of 2. That's fine. Because then I'm going to have square root of 2 over 2 times the square root of 2 squared. Square root of 2 squared is going to give us 2. And then 2 times 2 gives us 4. 2 root 4 being our final answer. For this very last one, we're going to simplify that to the square root of 11 over the square root of 13. We want to clear those denominators, so multiply both by root 13. 11 times 13, that's going to give us, I believe, 143. And then square root of 13 squared is just going to simplify to 13. So we have square root of 143 over 13 as our final answer. So just to recap a little bit, it can always be a strategy to totally prime factorize. And then whenever you're doing prime factorization, you want to keep this in mind, that whenever I have the index and the root matching, if that index slash root is odd, then those will directly just cancel out to leave us with the number. If that index slash root is even, then we'll be left with the absolute value of the number, aka the positive version of that number each and every time, because for even powered roots and even powers, you always end up with pairs of negatives being multiplied by each other and effectively becoming positive. For that same reason, if you ever have a negative underneath an even powered root, it does not exist. And by convention, we usually like to clear any roots in that denominator by multiplying both the numerator and denominator by that root, which will make us be able to exploit that same rule we just talked about how they cancel out, so that you will no longer have any roots in your denominator. And that's just a convention that we like to do. So, and also just for a little bit of vocabulary, remember that we have the radicand is the number underneath the root, and the radical sign is such that the index on the radical tells you how many times you're looking for a number times itself to give you that radicand.